Hello everyone, and welcome back to the AI Fundamentals course. I'm thrilled to have you here as we continue our journey into the fascinating world of artificial intelligence.
In our previous chapter, we laid the essential groundwork by exploring the overarching landscape of AI. We saw how artificial intelligence serves as the broad field, aiming to simulate human intellect. From there, we narrowed our focus to machine learning, understanding it as the subset where systems learn from data by discovering algorithms rather than being explicitly programmed. And we ventured even deeper into deep learning, recognizing its power through numerous neural layers to handle complex tasks like vision and speech. Essentially, we looked at these three concepts as the fundamental building blocks of intelligent systems.
Today, we're going to zoom in and solidify our understanding of the core concept itself. What exactly is artificial intelligence? We'll dive into its fundamental goals and capabilities. So, on this slide, we begin with a straightforward but powerful goal. The central aim of artificial intelligence is to make computers think and act like humans. To put it more formally, AI is all about creating intelligent machines that can perform tasks normally requiring human intelligence. This isn't just about crunching numbers. It encompasses a wide array of sophisticated abilities. As our diagram illustrates, this includes learning, the ability to acquire knowledge and skills, problem solving, finding solutions to complex issues, perception, interpreting sensory information, whether it's visual data from a camera or audio from a microphone, language understanding, comprehending and processing human language, decision-making, making choices and judgments based on available information. These are the fundamental capabilities that AI systems strive to achieve, bringing us closer to truly intelligent machines. On this slide, we'll explore the two main goals of AI that have historically driven research in the field. First, let's look at the left side, thinking humanly. As the icon of the cognitive brain suggests, this goal is about building systems that think exactly like humans. The focus here is on the process of thought itself, not just the final answer. This approach involves creating cognitive models to understand how the human brain actually processes information and makes decisions, drawing heavily from fields like cognitive science and psychology. Now, let's turn to the second goal on the right, acting humanly. This goal, represented by the robot icon, focuses on a different aspect, building systems that can perform human-like behaviors. It's less concerned with whether the system thinks like a human, and more concerned with whether its actions are indistinguishable from a human's. The most famous benchmark for this goal is the Turing Test, which we'll discuss in detail on the next slide. To succeed, this approach relies on key components like natural language processing for communication, knowledge representation, and machine learning to adapt.
Continuing our discussion on AI's goals, we arrive at a cornerstone concept for acting humanly, the Turing Test. Proposed by the brilliant mathematician Alan Turing in 1950, the Turing Test is a thought experiment designed to assess a machine's ability to exhibit intelligent behavior equivalent to or indistinguishable from that of a human. As you can see in the diagram at the top, the test involves three participants. A human interrogator, labeled as Alan Turing himself, communicates with two unseen entities. One entity is a computer. The other entity is a human, serving as a control. The interrogator exchanges text-based messages with both the computer and the human. If, after a period of conversation, the interrogator cannot reliably tell which is the computer and which is the human, then the computer is said to have passed the Turing test. This test doesn't merely measure a computer's ability to process information, it measures its capacity for intelligent behavior equivalent to, or indistinguishable from, that of a human. To successfully pass such a test, a machine would need several key components as listed below. Natural language processing for effective communication, knowledge representation to store and access information, automated reasoning to draw conclusions and answer questions logically, and importantly, machine learning to adapt and generate responses that feel natural and human-like.
Now, let's shift our perspective from simply mimicking humans to a different, more formal goal: thinking rationally. This approach aims to build systems that think rationally, which in the context of AI essentially means thinking logically. The primary focus here is on making correct inferences and drawing valid conclusions. It's not about how a human thinks, which can sometimes be irrational or emotional. It's about building a system that follows the rules of logic perfectly. The main approach for this is to use formal logic, much like in mathematics, to represent knowledge and reason about the world. However, this method faces a significant challenge. The real world is messy, uncertain, and full of nuances. Translating this complex, real-world information into the precise, black-and-white terms required for formal logic is incredibly difficult. For example, how do you logically define hot or happy in a way a computer can perfectly understand in every context?
Shifting from thinking to acting, our next fundamental goal in AI is acting rationally. This goal aims to build systems that act rationally to achieve the best possible outcome. Here, the focus is purely on the actions and their effectiveness in reaching a specific objective. Central to this concept is the idea of an agent. In AI, an agent is simply anything that can perceive its environment through sensors and act upon that environment through effectors. A rational agent, then, is one that acts to achieve the best expected outcome given the information it has. It strives for optimal performance in its designated tasks. The key advantage of focusing on rationality in action rather than trying to perfectly mimic human thought or behavior is that rationality is more general. It doesn't require us to replicate human errors, biases, or limitations. An AI acting rationally might perform a task in a way no human would, but it would do so optimally. We see this principle applied in many advanced AI systems today. For example, in a chess-playing AI, acting rationally means making the mathematically optimal move, not necessarily the most human-like one. In self-driving cars, the AI acts rationally by making the safest and most efficient navigation decisions based on real-time data. Or in smart building management systems, it acts rationally to optimize energy consumption and comfort levels. These systems exemplify the power of acting rationally to achieve superior results. Now that we understand the core goals of AI, let's take a quick journey through its history, starting with the early foundations. The idea of artificial beings isn't new at all. As the Ancient Roots section highlights, the concept goes back centuries, rooted in Greek myths and mechanical automatons. Humans have long dreamed of creating intelligent or autonomous entities. However, the true scientific and computational groundwork for what we now call artificial intelligence began in the 1940s and 1950s with the emergence of electronic computers and groundbreaking theoretical work. A pivotal moment came in 1950 when Alan Turing, a visionary British mathematician, published his seminal paper, Computing Machinery and Intelligence. In this work, he introduced the famous Turing Test, which we discussed earlier, laying a fundamental benchmark for machine intelligence. Then, in the summer of 1956, a truly defining event occurred, the Dartmouth Workshop. This landmark conference, organized by figures like John McCarthy and Marvin Minsky, is where the term artificial intelligence was officially coined. It brought together leading researchers and essentially launched AI as a distinct field of scientific inquiry. These early years were filled with optimism and foundational ideas that continue to influence AI today.
Following the promising beginnings, AI's journey through the subsequent decades was marked by periods of both rapid growth and significant challenges. In the 1960s and 1970s, there was considerable early enthusiasm. Researchers developed some of the first AI programs, such as ELIZA, an early natural language processing program, and SHRDLU, which could understand and execute commands in a simulated block world. The focus was heavily on logical reasoning and what we call symbolic AI. However, the reality soon set in that the early promises were often too ambitious given the technological limitations of the time. This led to a period known as the AI winter in the 1980s. As our visual depicts with the broken robot, this was a time of reduced funding and skepticism. Researchers faced significant limitations in computational power and the amount of data they could process, making it difficult to scale their promising but small-scale demonstrations. Fortunately, by the 1990s and early 2000s, AI began its resurgence. This revival was fueled by crucial advancements, a significant increase in computational power, and a shift in focus towards more specific, solvable problems and expert systems. This era also saw the rise of more practical machine learning techniques, setting the stage for the explosive growth we've witnessed in recent times.
And this brings us to the modern era of AI, characterized by explosive growth and the revolutionary impact of deep learning. The 2000s to the present day have witnessed an unprecedented acceleration in AI capabilities driven by a confluence of critical factors. Firstly, the advent of big data, the sheer availability of massive data sets. Modern internet, sensors, and digital platforms generate incredible volumes of information, providing the fuel that AI models need to learn effectively. Secondly, equally crucial is powerful hardware. The development of graphics processing units, or GPUs, originally designed for gaming, proved to be perfectly suited for the parallel processing demands of complex AI algorithms. This hardware provided the necessary computational muscle. These two factors, vast data and powerful computing, paved the way for the groundbreaking advancements in deep learning. This technique, built upon highly layered neural networks, achieved state-of-the-art performance across a wide range of tasks that were once considered intractable for machines. Deep learning has been the engine behind many of the AI applications we now take for granted, including highly accurate image recognition, allowing computers to see and understand visual content, sophisticated natural language processing, or NLP, enabling machines to comprehend and generate human language, and real-time speech recognition, powering virtual assistants and voice interfaces, and incredible feats in game playing, such as Google DeepMind's AlphaGo, which defeated world champions in the complex game of Go. In this modern era, AI has truly moved from being a theoretical pursuit in research labs to a powerful, pervasive force in mainstream applications, fundamentally transforming industries and daily life.
And that brings us to the conclusion of our foundational look into what is artificial intelligence. To summarize our key takeaways from this session, First, we established that AI fundamentally aims to build intelligent systems capable of complex tasks. We explored that these systems are driven by distinct goals, whether they are trying to think or act like humans or to think and act purely rationally. We touched upon the historic Turing Test as a significant benchmark for AI's ability to act humanly. And finally, we traced AI's rich history, from its ancient conceptual roots and the initial optimism, through periods of challenges like the AI winter, culminating in today's rapid and transformative advancements powered by big data, powerful hardware, and deep learning. It's clear that AI is not a static field. It's a dynamic, ever-evolving frontier. The breakthroughs we see today are just the beginning.
Now, before we conclude, it's time for you to put your knowledge to the test. To reinforce everything we've covered in this session, I've prepared a set of interactive multiple-choice questions. You'll find the link to this interactive quiz, along with the full set of presentation slides, right there in the YouTube video description. Just click on the link and it will open up in your browser. Each question will appear one by one, allowing you to select your answer, get immediate feedback, and then proceed at your own pace. It's a fantastic way to solidify your understanding of these core AI concepts. Please feel free to take the quiz as many times as you like to truly master the material.
And with that, we've reached the end of our session. Thank you for joining this exploration into the basics of artificial intelligence. We truly hope this session has provided you with a solid understanding of what AI is and its fascinating journey so far. The world of AI is continually evolving, full of incredible possibilities, and your curiosity is its greatest asset. Stay curious and keep learning. It's been a pleasure to guide you through these foundational concepts. Goodbye for now, and we look forward to seeing you in our next tutorial.